All right, welcome back. So now we're going to combine a lot of the things that we've been setting up over the last few lessons. Over the last couple of lessons, we've introduced ideas such as the ambient pressure, the hydrostatic pressure, aka the gauge pressure, according to the current CED and equation sheet for the AP exam, but I know it more prominently as the hydrostatic pressure, and the dynamic pressure. Now, we talked about basically a little bit on how to work with each of those equations, but honestly, we didn't necessarily go into a whole lot with them because what they really do is they combine into what we're going to take a look at today, which is a very important topic, depending on what things you might actually go into. So we are going to talk about Bernoulli's equation. Now, this is kind of, well, one of the key focuses for the fluid mechanics section. And most of the questions that I've seen, not all of them will be this, but many of them are related in one way or another. Bernoulli's equation is something that has broad applications, especially if you're interested in things like civil engineering or aerospace engineering in particular. Not saying that it's not applicable in many of the others, but I know in civil engineering there's a lot of things often with some focus of it when you look at plumbing or other fluid flow for water infrastructure. And then my personal background was actually in, I did a design sequence in aerospace engineering, and we looked at that not so much as water flowing, but instead as air flowing. Remember, fluid is both liquid and gas. Now, I can say Bernoulli's equation applies beyond the scope that we're going to introduce here, and part of that is implied by some of the connections that we'll draw with where Bernoulli's comes from and what it's actually a viewpoint of. But I will point out for anyone watching this and looking to go to the higher levels or involved in, say, a full university class where they may not have the same limitations that we have in the setup for the AP exam, or I guess if AP changes it in the future. We will be looking at Bernoulli's equation applied specifically to what's called incompressible flow fields. In other words, we're looking at a fluid that the density remains constant. Okay, now that that disclaimer is out of the way, and a little bit of introduction to help emphasize how important Bernoulli's equation is. Depending on what you go into as a profession, this may be the first time you see it, but you may be applying it for the rest of your life. And even if you aren't looking at it from a professional viewpoint, understanding Bernoulli's equation can give you a lot of understanding of a lot of things that you interact with on a regular basis. Okay, so while I'm certain there's a textbook definition for this, I'm going to summarize what the best ways to be thinking about it. Broadly, what Bernoulli's equation is energy conservation applied to fluids. Now, that could be fluids in motion or even stationary fluids. As we're going to see in our analysis, we kind of have the ability to apply this in multiple ways. However, what we will see is we apply it to one set of fluid for the most part that's directly connected so that we can see that we've got basically a constant value, a quantity that applies to all parts of that connected fluid. In fact, that's the other part that I've got for my definition. So broadly, when you think Bernoulli's equation, this is the most thorough way of describing it. It's basically energy conservation applied to fluids. But we could also see it as, I'm going to grab my makeshift notes here, it is a constant value for connected fluid systems. I'm going to add a little bit onto my makeshift notes by saying that it is, or relies upon, is affected by fluid height, flow speed, and ambient. I'm going to go ahead and extend the page here, if I can. Pressure. Okay, pause there for just a moment. I'm going to go ahead and move this over and take a look at the AP equation sheet. So in this case, Bernoulli's equation, being a statement of energy conservation, is usually how I describe it, and usually how I teach it as well. In this case, energy conservation usually starts off with the idea of, I'll go ahead and draw that in here. We've got it would have our initial energy is equal to our final energy. And that's something that we've taken a look at a lot in my class and in the studies. So if you've been following along with my other lessons, this probably will look very familiar because we've done this repeatedly through both our energy section and our momentum section whenever we're dealing with a conserved quantity. So Bernoulli's equation is basically energy conservation, not just a new conservation law, but specifically energy is what it's related to, as we will see. But we had originally where we would have the initial mechanical energy, say the gravitational potential energy, plus the kinetic energy equaling the final energy. Well, the same thing is basically happening here as we look at different points in fluid flow. So I'm going to write this as it appears on the AP equation sheet. We've got pressure 1 plus rho g y1 plus 1/2 rho v1 squared equals the same thing at another point. Pressure 2 plus rho g y2 plus, I'm running out of room here, 1/2 rho v2 squared. Some of my materials, y is probably the better representation. This is a vertical height. But in what we had, in fact, I'll pause here for just a moment, this pressure is the ambient pressure. That is the pressure of the surroundings of the fluid. This term is your hydrostatic pressure, or as the AP exam is currently calling it, the gauge pressure, although they've got it marked as rho gh. But it's basically the same thing where we have the height or the vertical distance above a given reference point. But that's our y. And then finally we have our dynamic pressure here as well. This is why it's the combination of our last few lessons where we've got the ambient pressure, the hydrostatic pressure, and the dynamic pressure. These are the three common types of pressure that show up in our flow fields. So, running through, I'll go ahead and write in our key on this. We've got the first pressure, P1 or P2, I guess I'll do P star, is our ambient pressure. At that point. This is, for want of a better term, in fact, I'm even going to put it in here, this is usually, though not always, atmospheric pressure. If you have something open to the atmosphere, then the ambient pressure is just the atmospheric pressure. And you can set that to 0 and make this, all the rest of this, gauge pressures, because they would be measured against the ambient pressure, the atmospheric pressure. But this is basically our initial pressure from the outside, say, air or conditions squeezing the fluid. Then the next term that we've got, so we've got rho, density of fluid, and I do want to emphasize, while we have a bunch of spots for the density to go in here, we do not have it where the density should be changing, at least by my recollection on this. I think to have a changing density for Bernoulli, you might have to get a little bit more complex with these. I'm getting flashbacks to my aerospace engineering classes where we were warned repeatedly that Bernoulli's equation begins to break down, at least in the way that we were applying it, when the airspeed of the aircraft ended up above about 0.3 Mach. And so that's not something that you would need for my class or the AP exam, but I do want to bring this up, that as you go to the higher levels, this is an introductory class, but as you go to the higher levels, you might deal with compressible flow. And while Bernoulli's can apply there, it starts to get much more complex than this equation. Okay, G is the local acceleration due to gravity, or accel of grav, or also phrased as the gravitational field strength. We've also got Y1, or as you'll notice in my materials, I'll have like H1. This is the vertical height, location, or depth. Now it seems a little confusing, but it's one where when you start working with it, it'll usually make sense. Let's see. We'll see a couple of examples as we go through. I don't want to get too mired in this. We've already done rho. So finally we have V star. H1, I guess this is Y star, and H star, where it could be any of the values there. But V is fluid speed at that point. And I guess these are vertical height at that point. Okay. Brief rundown on the units, though everything is in SI, so we would have our fluid speed is in meters per second, our vertical height is in meters, we would have the acceleration due to gravity, which would be in either Newton per kilogram or meter per second squared. Both of those are perfectly fine. And then fluid density would be in kilogram per cubic meter. And then finally, our pressure would be in Newton per meter squared. Okay, so again, these are the SI units. They are what you will preferentially want to use. Okay, so that was a breakdown of that. Here's where I want to show you a little bit more to tie this together to realize that we are dealing with something related to the energy. In fact, let's find out. I keep saying something related to the energy, but it's not actually the energy. So maybe we should look at why or how that ends up working out. So we're going to say the following. Let's go back to a value for energy, where we would say that our energy at a given point, our total mechanical energy, is going to be equal to our kinetic energy at that point, plus our gravitational potential energy at that point, plus our, I'll go ahead and add a spring potential energy at that point. But here's what I'm going to do. For the fluids, we would have, next line, my total mechanical energy would therefore be 1/2 mv squared, that's my kinetic energy, plus mgy, where y is a vertical height above a reference point or with respect to a reference point. So this is my gravitational potential energy, and I'm going to leave this as my spring potential energy, but there's a reason that I'm going to have it in there for us to kind of take a look at. Now the thing about this is, with fluids, we've got so much of them and they move around, we're looking at different points of the fluid, not all of the fluid at the same time, and that's where we run into issues with the idea of the mass. Now, we're used to applying energy conservation onto an object that's at one spot and then you move it around. But we're going to be looking at fluid flow, like water flowing through a pipe, and while the water itself actually moves from one place to another, if we just kind of watch it, we've got parts that are moving, but the system never really changes overall. And that's where we bring in the more advanced classes, you'll see things like control volumes as a way that we actually apply the idea of system definitions onto fluid systems. That being said, I'm going to kind of simplify this. And the thing that I'm trying to draw on your attention to is we don't really have one object that we're looking at in fluid flow, so we don't really have the mass itself. But what I do actually have is the following. So here's what I can do. I could say, instead of having just one object, I could look at the amount of fluid that I have in a given volume. This is a reference to that idea of a control volume, which is fancy talk for the upper levels. But here's what I'm going to do. I'm going to divide both sides by volume. So I'm going to multiply by 1 over capital V for volume in this case. Well, what does that give me? This gives me that I've got, go ahead and switch my color. My energy divided by volume, we'll come back to that, equals 1/2. I'm going to take my mass and put the volume underneath that. All of these are multiplied, so I could multiply or divide any of them by the volume, but I'm going to take and find the masses in particular. So I'm going to take, I've got my mass divided by volume times gy, plus I finally have some term here, which is a spring potential energy divided by, I'm getting ahead of myself, a volume. Now that last term is going to be more of a hand-wavy one, but I'll describe the conceptual ways and hopefully it'll tie it together. But I end up with some energy divided by volume, which equals, well, mass divided by volume is just our density. So m divided by v would give me my density, 1/2 rho v squared, plus I've got m divided by v, well that would be rho gy, plus some value over here, which is some spring potential energy, effectively, divided by a volume. Now why do I say that that's a spring potential energy? Well, let's think back to the ambient pressure. The ambient pressure describes how much the surroundings are squeezing your system. That's kind of like a spring. Well, if I take a spring and I squish it and I put it right next to your head, it's going to push on your head. If I put them on both sides, it will squeeze your head, for instance. Now, that pressure can be applied over a displacement under the right circumstances, doing work, releasing energy. And since we have energy that it could release, work that could do from being squeezed, that's what this term represents. So we have something that is broadly describing a pressure. We got something that's squeezing, much like a spring would, and because it's squeezing, it can apply a force that can add or remove energy to our system. So this last term is actually very similar to a spring potential energy. We just don't have one spring, we have all of the atmosphere or the surrounding container that is squeezing the thing in not dissimilar way to what a spring does. So all we have with Bernoulli's equation is it's applying energy conservation, as we can see here, onto a fluid, but because fluid flow and fluid systems are a little bit trickier, we can't look at the total energy, we look at what's called the energy per unit volume. That's weird. Okay, let's think about that for just a moment. If I have energy per unit volume, that would give me the following units. I would have a joule per cubic meter. But with the work equation, a joule, work, energy, is done by applying a force, Newton, over a displacement, times meter. So I could actually replace the joule with a Newton over a meter, or Newton times meter, I should say. I'm emphasizing that that's different than torque Newton meters, just as a reminder on that, if you've seen it. But a force applied over a displacement, Newton times meter, is how you would do work, which is energy, a joule. So I would have the following, but 1 meter can cancel out with this, leaving it squared, and I end up with Newton per meter squared, which is a Pascal. So my energy per unit volume is actually in units of pascals. One of my professors actually pointed this out to me, and he said, Sanchez, pressure in many ways can be viewed as an energy density. Remember I said that there are many types of density. Here's another one. This is a volumetric energy density. And this actually applies in a bunch of systems. As you go forward into things like thermodynamics or other studies that you may have, this might prove very useful, and that's why I want to stop and talk about it. What's pressure? Many times it boils down to an energy density. If you add more energy into a given amount of space, well, if you look at your ideal gas law, for those of you familiar with it, you'd be adding energy in. Most likely that would go into thermal energy, so the temperature would raise, and you would therefore have, for a fixed volume, but higher temperature, you have an increase in pressure. You can also check out our materials in Unit 9, I believe, which is in the After Newton section of the website, when that is actually posted. But we'll also talk about thermodynamic applications for AP Physics 2. All right. Now that we've introduced a lot of that, let's take a look at actually applying these ideas. And for that, I'm going to check on my recording and get us set up with, I will show you real quick. I went back to try and find some old AP questions for us to take a look at. That seemed like a good approach on it. However, one of the things that I ran into was most of the ones that I could find actually had us apply what will show up in our next lesson, continuity equation, the very last of our fluid mechanics studies. And so basically, most of the problems that I found, we could do parts of them, but not all of them. I went back and found one of my old techniques that I used in my class that I refer to as group problems. And it's one that has what I feel to be a very realistic application about supplying water to a high-rise building. And so we're going to take a look at a little bit of plumbing, for want of a better term. But in doing so, it'll give us an example to take a look at for applying Bernoulli's equation. All right, back in a moment. All right, and we're back. So let's see how we can apply Bernoulli's equation in a type of sample problem. In this case, I'm going to read over the broad strokes of this, but I'm not going to read the entire thing. Man, this thing is old. I think the last time I used this was almost 10 years ago. So you are the building manager for an apartment complex downtown. The building you manage is 7 stories tall, about 25 meters. Tenants on the 6th floor and above have complained that the water pressure is too low. The 7th floor is an attic storeroom, so you don't actually have tenants on the 7th floor, so it's the top floor that you're actually having to care about. That's not really important for the problem itself, but it's kind of building the realism of it. In short, they're claiming that they want the water pressure to be higher to represent that. I've given us the goal of saying that they claim they want the water speed when they turn on the faucet to be about 3 times faster when it actually comes out of the faucet from what it currently is. Right now, what they've got is, and this is not uncommon if you do not have a tall building, you would have maybe a water pump that then pressurizes the water so that it could actually be sent up to the higher levels, as we're going to see as we apply this Bernoulli stuff. In this case, I claim that the pump at the ground level is supplying a pressure onto the water source of about 306,000 pascals. That's about 3 atmospheres. And we're going to say that that's a sealed system, so we're not necessarily looking at ambient pressure from it being open to the air necessarily there. We're going to see when we set that up. A shower head on the 6th floor is at a height of 20 meters above the water pump. In this case, what you've decided, and this is actually pretty common, in fact, if you live in a much more urban area with many high-rises, take a look at, or even if you don't, Google it, you'll actually find a bunch of pictures of the tall apartment buildings, and at the top, there's a bunch of water towers in them. When we get to the end of this problem, we'll talk about why this is actually a really good solution, and how even if you don't live in a high urban area, why there are so many water towers around in general, and some additional applications of it. But in this case, here's what we want. We want to take our current system, find out what the water speed is, and we're going to try and triple that water speed by putting a reservoir up on top of the high-rise building. So, coming back over here, I didn't come to a new slide, but we'll go ahead and draw this out, even though I've got a picture there. But real quick, we've got a building here, and we've got a pump down here, and I'm going to call this position, let's call it A. And then we've got water that is pressurized and then goes up over here and then out at this location. And then we've got that this is 20 meters up. We're dealing with regular water. We are going to try and replace this system with a different one, but we'll draw that a little bit later. In order for us to go through and actually try and triple the speed of the water, we could either derive the solution, although that becomes problematic because I've been given that the pressure supplied at point A is 306,000 pascals, or 306 kilopascals, as the case may be. You can actually do a derivation on that, but you're going to end up with just a whole bunch of terms, so this is one that might be better solved with numbers, and it's the numbers that I've actually given. Okay, so here's what we can do. I've defined a point A, and then I'm going to compare that to some other point, B, up here at the water faucet. Okay, so what we want to do is, with Bernoulli's equation, we want to do a comparison of the pressures at various points. Now, in this case, usually the water pump, even if water is actually coming through, the pump brings more water in, and so for our purposes, we're going to treat this as though the pump is pressurizing the water as it sits there, and everything remains pressurized until someone actually opens the tap. So here at the bottom, at A, we're going to say that the speed at point A is effectively 0. The other thing about that is the faucet that we turn on is going to be super tiny. The pump is actually probably going to be applying its pressure onto, say, like a water main, something where it's really, really big. Something similar to this happens with water heaters as well in houses and other, I guess, most buildings if you have hot water. Okay, so we're going to say that this also is my reference height, that we're starting off at y equals 0, and that makes this y equals 20. Okay, great. So now here's what I can do. I'm going to compare my Bernoulli's equation at point A. Now, I'm going to shorthand this as the energy at A equals the energy at B, but as we just saw before we came over here, it's more accurate to say the energy per unit volume at A is equal to the energy per unit volume at B. And please note, I've drawn this out so we can see that these 2 points are connected, so that's an important thing. You can't say we've got pressurized water from the pump here and then there's a pond outside that isn't actually connected in the flow field in any way, shape, or form. They will have different energy values. So we can only apply this when you have connected parts of the water flow. Okay, so with this, I'm going to have the following. The ambient pressure at A plus the hydrostatic pressure at A, plus the dynamic pressure at A equals the same values at point B, plus rho GHB plus 1/2 rho VB squared. Okay, here's where, and I do want to emphasize this, especially with our first one, solving with numbers. You've probably seen in most of our lesson stuff that we introduce the materials. we'll solve at least one problem with numbers, and then we usually do some derivations. And I don't know if we're going to do a derivation on this one, but you'll see some, especially in the next few sample things as we go, but hopefully this gets you what you need. Okay, the ambient pressure. Well, in this case, that's the pressure that the pump is applying onto the water. And so we were told, okay, my timer didn't actually go, so hopefully everything's going to be fine on this. Let's see. The pressure is 306,000 pascals plus rho, which is 1,000 kilogram per cubic meter, we're dealing with water, times G, we're going to use the AP simplification with 10 Newton per kilogram, or 10 meter per second squared, and I need my height at position A, or YA. In this case, I'm setting that to be my reference height. Remember, this functions a lot like gravitational potential energy, so we can define our y equals 0 or h equals 0 wherever we would like. In this case, the hydrostatic pressure starts to get a little bit trickier on that, since we had introduced it as the height below the surface. That's if you're just dealing with what it is down at the bottom of some sort of depth. But since we're applying energy here, all we need is to be consistent so that we can see what we've got here. Okay. So now that I've got that, I now have plus 1/2 rho, which is 1,000 kilogram per cubic meter, times VA squared. Well, I said that basically our flow speed there is effectively 0. All right, so when I put all of these together, I can set up and make it directly equal to the other point, but since we have all of the numbers, let's go ahead and solve for that. We get the following. This has multiplied by 0, this has multiplied by 0, and because of the simplifications we're using, but they still closely represent real life, we end up with an Bernoulli's value of 306,000, in this case, pascals. In this case, because we had no hydrostatic pressure or no dynamic pressure, the pump is the only thing supplying effectively energy, an energy source for our water system. If you had no pump, then you would have 0, and that's where we wouldn't be able to actually lift any of these materials up to the locations that we want them to go, or to get them moving with the speed that we want them to. Okay, now that we've got that, we can now set this equal to our second point. 306,000 pascals must therefore, this is the value at A, we're going to set that to the value at B. So at B, we have, let's start with the ambient pressure. When I open the tap and water starts flowing out, I have a sink over there, sorry. You all can't see that in the video. But when I open it up, the water starts coming out of the tap, and it's not that it's at 0 pressure, because it's moving out into the atmosphere. So here's where we want to be very careful. Since the tap opens to the atmosphere, our ambient pressure is 101,300 pascals. 325, I think. But we'll take it to this just for our solution. Plus, let's see, rho GH. Well, we've got 1,000 times 10 times our height now is 20 meters above our reference point. Plus 1/2 1,000 VB squared. And here's the thing that we're looking for. How fast is that water coming out of the tap? Now, we've got numbers for everything that we would need. We have 306,000 with appropriate units equals 101,300 plus, let's see, 10,000 times 20 would be 200,000. Let's see, plus 1/2 1,000 VB squared. So I guess that's 500. But we can move forward with this. Okay, so I'm going to do a little bit of math on this. 306,000 minus 101,300 minus 200,000 equals, so I'm subtracting these over, and I get 306,000 minus all those is a very small 4,700 pascals with the units that we had, equals 500 times VB squared. I divide both sides by 500, and I end up with 9.4. In this case, 500 does have units, I guess kilogram per cubic meter. When we work all of that out, again, here is why we have an SI system. Put SI in, get SI out. We'll end up with meters squared per second squared equals VB squared. Finally, we end up with VB being just a little over 3 meters per second. So I end up with 3.07, this board will be the death of me, 3.07 meters per second. That's how fast the water is coming out. Okay, now we've got a number that we can begin to work with. Setting this up, in real life, a tenant would actually say, hey, the water pressure is really low. We want higher water pressure than what we've got. For our purposes, I wanted to give us some numerical values that we could actually solve to design something. So while in real life, people wouldn't say, I want it to be going 3 times faster. They'd say, I want higher water pressure. It would be a number similar to this that a design engineer would go in and say, okay, we got to bump up our pressure on that, and we need it to be within these ranges. For us and our focus, it's common for both I and the AP exam to ask you about speeds, velocities, because that's a big focus in physics, and so that's why I've set it up with this. So now, part 2. We want the following. VB right now is equal to, let's call it just 3 meters per second so that we can cut down on at least a little bit of rounding on the calculations. It was 3.07, but what we really want is VB new, so I'm going to do VB prime, to be 3 times that. 3 times 3 meters per second is going to give me 9 meters per second. So this is what we want to redesign. So here's what we've got. I'm going to get rid of that old pump system, and we're going to say that we are now at, we said that this was y equals 20. You could reset your coordinate system if you want, but for completeness, I'm just going to keep us going with what we had before. We're now going to instead put a water tower is the plan. Now, one of the things that you'll notice is if you go looking for those pictures that I mentioned, the water towers aren't always just sitting right on the roof. Many times they're actually up on a stand of some kind. So we would have a whole bunch of water up here, and we would actually have it drop down and then go over to our target faucet through a series of pipes. Now we'll talk about how the water gets up there at another point, but for now, here's what we're doing. What we want to know is this. Where does I'm going to say the top of the water tower need to be such that we can get this outcome, that the speed at point B at a height of 20 meters above the ground is going to be 9 meters per second. Okay, so let's see what we actually need. Now, I'm going to go from point B, which is here at the faucet, and we're going to call this point C. It'll be kind of our new A, I guess you could think about, because we're moving things around, we're changing things to set up a new system, but to get the job done the way that we want. So you could also call this the new A, and this is the new B, but I like to keep notations that match spots, so I can just think, okay, B originally, or new B, that sort of thing. Okay, so here we go. Let's start off by finding our, once again, I'm going to call it energy at B, but it's actually energy per unit volume. So instead of doing equals, I'm going to say it's going to be related to this. We're going to have our new pressure at B plus, or I should say the ambient pressure at B plus rho G HB plus 1/2 rho VB squared. So now that we've got some of our numbers, we can start filling things in. My ambient pressure. Well, unless we pressurize the apartments, which would be bad, we're going to have that the tap opens to air any way you look at it. So my ambient pressure at point B is still going to be 101,300 pascals. Plus rho GH, well that's 1,000 times 10 times 20, because that's still measured. You could have changed it, but I'm going to keep things consistent there, so we're 20 above the ground. Plus 1/2 rho, that's 1,000, times 9 meters per second quantity squared. So the energy that I need, energy per unit volume that I want to get 9 meters per second squared, 9 meters per second at point B would be whatever we get here. So I'm going to multiply these out. So 9 squared is 81 times 0.5, let's see, times 1,000 gives me 40,500 for our dynamic pressure. Plus, once again, this came up to 10,000, 200,000. plus 101,300 because we're open to ambient pressure, atmospheric. 101,300 plus 200,000 plus 4,500, or 40, then 500. If I've done this correctly, my Bernoulli's value comes up to 341,800 pascals. Now, many times you just set point A and B equal to each other, or in this case, B and C. So you wouldn't necessarily have to solve for this number, but my board is only so wide, and we're dealing with so many numbers that it might help to stop and find one side, basically. Okay, now that I've got that, I'm going to set that equal to 341,800 pascals. I'm going to set that equal to what I need to do in order to get that value for my water tower. Now, one of the other things I'm going to say is this. For safety issues, you could have a pressurized water tower, but having a large pressurized vessel on the top of a building filled with heavy material might be bad. Many of these might actually be open to the air, and so they vent to the air. We'll talk a little bit later at the end of this lesson why that's probably not the case, but they probably keep it at least close to atmospheric pressure. So in this case, I'm going to say that our water tower is open to the air. If you want an example, maybe they're letting rain fill this up. Now, hopefully your water tap is not actually giving you rainwater, but your mileage may vary. So in this case, I'm going to say that for whatever reason, our water tower's internal pressure, or the ambient pressure, I should say, is 101,300. Plus, we're going to say that we're looking for the total height of the water up here, where we want to put the top level of the water. So that's going to be our YC or HC, however you'd like to write that. But we would have rho G YC plus 1/2 rho VC squared. I guess I should have done PC, pressure at C. Now I'll fill in the numbers. You could have easily skipped that step if you want, but remember on my exam or the AP exam, showing enough of the work can be useful if you put in just the numbers and you mess up on the calculator and this does not end up being what it should be. We have no idea what you're trying to do. Don't be afraid to take the extra step to send a clear message to me, the grader, what you're trying to get across and that you know to use the right equation. So that way if you make a math error, which is pretty common, you can still get credit. So on this we would have 1,000 times 10 times YC. I don't know YC, but that's what I want, plus 1/2, 1,000. In this case, the water tower is going to be like super big. We want it big enough such that when one person turns on the tap, it's not like the water tower just drains instantly. We're going to have it where it's going to drain super duper slowly. So this is actually pretty common where our VC is going to be effectively 0. Is it actually going to be 0? No, but it's going to be like a huge, not quite swimming pool size thing. So when I turn on my faucet or even take a shower, the water level will drain, but it's going to drain really, really slowly. So that number is going to be very low regardless, as long as I have a decent sized water tower, or decent sized reservoir is the technical term. Okay, so I would end up with plus 10,000 YC plus, well, 0. Okay, so on this, I can now solve for YC, the height that I need to have the water tower, basically the top level of the water tower up to. I can subtract this over. We would end up with 341,800 minus 101,300. And I would end up with, let's see, 240,500 equals 10,000 with appropriate units times YC. So I'm going to divide this by 10,000, and I end up with YC is equal to 24.05 meters, at least based on my analysis here. Okay, so I want the top of the water tower to be at a height of 24.05. Here's y equals 0. I said it was a 25 meter tall building, so we'd actually want to install this down in the attic space or very close to the roof itself. If I install it just straight up on the roof, that would be high enough to actually get the water pressures, at least by our definition of it, that we actually want here. Now, is this the actual values for a real life thing? I don't know, I'm not actually a building manager solving these, but I can tell you that how we would go about doing this is using these type of applications. one thing that we are ignoring, so far as I know, for the scope of this class is, and you'll see this when you get into an engineering fluid mechanics system, Bernoulli's equation, often, the one that we're working with, looking at it as energy, we're looking as though there is no friction in the system. And then one of the first things that you would add, even in an introductory fluid mechanics class, focused on fluid mechanics, there would be an additional term to account for the energy, effectively, that is removed by frictional effects. While water flowing through a pipe has very low friction, it doesn't have no friction. So as you move it through various pipes and stuff, you would end up with what's called frictional losses. We describe them as a drop in pressure from frictional losses, but when we understand that pressure is an energy density, functionally, we have that friction is going to take some of that energy, and therefore we would have less energy per unit volume, and therefore lower pressure. Okay? That's the sample problem that I wanted to work through with Bernoulli's. We're going to be back in just a moment to finish up and tie all of this together and get a little bit of understanding of why we do things the way that we do with our modern plumbing system. So back in just a moment. All right, one final thing that I wanted to run through. Applications of this. Now that we've understood this a little bit better, you can have, plumbing systems. Let's think about that. In order to have it where, I'm going to go ahead and turn on the sink again. You can hear the water flowing. Having a good flow of water and having good water pressure, as we saw in our example, we need to have some sort of source of energy, source of pressure onto that fluid so that we can actually push on it enough, squeeze it enough, so that it can go up to a higher height and still have a certain amount of speed, or have a certain amount of speed in general. So something has to supply that energy. And so one of the ways that you could do things, and a lot of people might not necessarily realize this, ignore the possibility of a water tower and think about having just a pump. Well, we could have a pump, a high-powered pump, that was actually pressurizing our entire water system, and therefore it would supply all the things that we need. Except what happens if we have a power outage? Well, if the power goes out, then the pump goes off, and we also lose water. Well, think about that. If you've ever been in a situation where the power has gone out, usually the sink and the toilets and all the water systems usually still work. Now, your water heater may turn off because it might rely on electrical power of some kind or another, but you still have water, and that's actually by design. I found this out when I was a bit younger, when I actually asked, I think either I asked or someone in my undergrad asked about it when we were studying some of these materials, or at some point, why are there so many water towers? Like, when you drive around, almost every single town, no matter how small it is or how big it is, has water towers. Here in the town that we're in Edmond, Oklahoma, we've actually got a bunch of water towers. In fact, for our school, we've got one right next door. In fact, I had a lab for a while that was measuring the height of a water tower. In fact, from the parking lot where I get out of my car, I can see 2 gigantic water towers. And there are even more spread around this small or relatively small city comparatively. So why are there water towers? Well, we tie those two ideas together and we have our answer. Ignore the pump for now. Let's say that we put all of our water up here in the water tower and it requires no electricity at all because it's just gravitational force. As long as we don't open the taps or anything like that, all of this pressure is maintained in that system. In fact, what we do is we don't have water towers actually open to atmospheric pressure. We don't keep them heavily pressurized because they're so large that the materials might be dangerous. But we do have them where they're actually set up there. And then what we'll do is we'll pump water in. We'll come back to that. So there are pumps involved. But even if we turn off the pumps, there's so much water pressure that at every given spot in our system, away from the water tower, we actually have a pressurized system. We've got so much water pressure on this, and this is one of my favorite things. If you've gone without power for a very long time, after a couple of days, the local authorities will issue a boil notice. What that means is they say, okay, if you get water from the tap, that's fine, but you should boil it first before trying to drink it or cook with it or do anything with it. And that's one where, if you've never thought of that before, stop and think about why. Why is it our water is so safe to drink if it's been in pipes for quite some time? What if there's a hole in a pipe? Well, that's why we keep our system pressurized. It's pressurized noticeably above just ambient conditions, especially down here, because we need that pressure to get the water pressure that we want, so it isn't just a trickle whenever we turn on any faucets. So we actually have a good amount of pressure down here and throughout most of the system. Up here, there's less pressure, but it's the hydrostatic pressure that actually builds up a lot of the pressure throughout our system. And so if we had a hole in a pipe here, the pressure in the fluid in the water part of it is so high that all that water will, if there's a hole, water will be constantly spurting out of it. So you can't really get germs or diseases or bad things to go back in because they would have to somehow push past a giant torrent of fast-moving, high-pressure water. By keeping the system pressurized, we actually keep it sanitary and safe. That's why we have safe water that we've put up in the water towers that you can drink without any problems about diseases or anything like that. And as long as the system stays sufficiently pressurized, we don't have to worry about it, because anything that would try and get in can't because of the intense pressure that it goes up against. But if the power's been out for a long time, the pump shuts down, and as everybody uses water, the water level begins to drop. Well, what does that do to our hydrostatic pressure? Well, as the water level drops, we have less hydrostatic pressure, and therefore the pressure in the system becomes low enough that if there is a hole in the pipe, the water isn't pushing out hard enough that maybe something could get in. And therefore the water is not necessarily safe. That's why if power goes out for about a day or so, you don't hear anything about, oh, you should boil your water, because it's still high enough pressure that everything's safe. But as time goes on, they may issue a boil notice that tells you that, hey, your water's probably safe, but we can't be absolutely certain, so you should actually boil it to kill any microbes or anything else bad in there that might end up poisoning you. So that's a little bit on how our system works. The other thing that is nice about this is, if I didn't have a water tower and I just had a pump, it would have to constantly supply a lot of energy every time someone opens the tap. In other words, this thing would have to be super powerful and be going almost all the time. But having a water tower instead, here's one of the things that I absolutely love. You can actually see, sometimes, I've heard before, the Super Bowl, when that happens in the United States, you can actually see water pressure of the system change in real time. Like basically turn on a tap, and if you look extra close or set it up right, you can actually see whenever a commercial break happens during the Super Bowl, because that's when a bunch of people will get up and use the restroom. And everybody flushing the toilets at the same time draws a lot of water, and there's a slight, very slight, not unsafe, but a very slight decrease in the water level. If you didn't have a giant reservoir to pull from and you had a pump and everybody flushed the toilet at the same time, well then the water pressure would completely collapse, and faucets would stop running water, the toilets wouldn't refill, at least for a while, until the pump could get caught up on it. In short, you can take a lower power pump and have it where it is just taking the water coming in from, say, a treatment plant, where it's nice and clean and ready to go, and it will put, I don't know, maybe a gallon every second up into the giant water tower. Instead of having a gigantic pump that needs to do 1,000 gallons per second so that everyone in the city would have the water they want. In this case, we can basically have it where instead of doing a whole bunch of work at once, we do a small amount of work all the time. So this pump is lower power, but just keeps running to keep filling up the water tower. And when everyone wakes up in the morning, when it's a high water draw period, where people are brushing their teeth, using the bathroom, taking a shower, that sort of thing, the water tower will actually drain down, but then they go to work, go to school, they do all of that and stop using near as much water. Or also you could say the same thing at night. People take a shower, brush their teeth before they go to bed, and then throughout the night, very few people are using the water, and so through the night, in the low demand periods, this pump is still slogging away, just putting a small amount of water in every second, and it will refill it when there's low demand. In short, the water tower is such a great way of approaching so many of our real-life problems that is why you still see them everywhere. If a new development gets set up, there'll be plans at some point when there are enough houses that a new water tower will go up, and this is why. It allows us to have a pressurized system to keep our water completely clean and reliably safe, And it also allows us that if there's a power outage, we don't immediately lack access to water, which is something that is even more, well, that's honestly very dangerous. Lack of access to power can be dangerous, but usually not as much as not having any water. So I wanted to finish up with this and really give you an understanding. Next time you see a water tower, be thinking about that, but this is a marvel of engineering and creativity in how it works to solve our problems. And this is a very real-life application of Bernoulli's principles. And a scaled down version of this happens inside your house or apartment or wherever you live on a regular basis, even with things like the hot water tank or the water heater, and then supplying hot water to different parts of the house and so forth. So you end up with a large reservoir, usually a little bit pressurized for a variety of reasons. But here are some applications of Bernoulli's equation that get me really excited about knowing about this, because our modern society could not be possible without these applications of it. We wouldn't be able to supply water in the way that we do. All right, until next time.